Swayam Prabha. Digital India. Educated India.
So, in this lecture, I will be talking about multi-component introduction. This is a very vast field, but we will do a quick a mini introductory level discussion. So far, all the problems we discussed in distillation are binary. Okay, so there are two components. One of them is more volatile than the other, and we looked at various design principles. But in many industry relevant distillation operations, we usually have multi components. This is because you have to see that these mixtures are coming from a reactor, let's say, okay, where there may be a desired product and undesired product. There will be a mixture of many things. So, in principle, we should be looking at a design principle of multi-component distillation. But since this is an undergraduate course, we may not be able to do multi-component distillation in very detail. But it is also good to kind of think about what additional challenges exist when we deal with multi-component distillation. So, that is the context of this lecture. So, for illustrative purpose, we will think about a ternary mixture. Let us say we have A plus B plus C. Okay, there are three components in the liquid mixture, and we will assume that the relative volatility of A is more than B and which is more than C. Okay, so that means component A is highly volatile, component C is non-volatile or less volatile, and B is something in between. Okay, so this is the order in which we will deal with it. Now, when we think about separating A, B, C nearly pure products, we have to think about some design principles of combining multiple distillation columns such a way that you can achieve nearly pure A, B, C separation. Okay, when we think about this design, there are so many options and choices we have to make. So, let me give three different examples for separating just this mixture and see how many possibilities arise. And then we have to think about which are more optimal with respect to cost, with respect to the ease of separation, and with respect to spatial requirement and so on. Okay, so many times we have to make decisions based on economical considerations also. For this particular problem, let us say I have this particular setup. So, here the feed contains all the components A, B, C with certain mole fractions. We can have a scheme or a topology of the design such a way that we have the first distillation column in which predominantly A and B are the top products. Okay, the temperature and pressure, this can be adjusted in the column 1 such that the distillate of the first column is rich in A and B and very lean in component C, whereas the residue will be much more richer in component C, but it may have tiny amount of component B and even more tinier amount of A. Okay, as you know that in distillation we can't get 100% pure component, but we can only minimize the impurities. Okay, so the separation that is going on in the first column is that residue in a nearly pure form comes below as a residue with a little amount of B and even more little amount of A, whereas in the top it is predominantly A and B mixture, and A and B can be in quite significant compositions. And then what we do, we take this A plus B rich binary mixture, send it to column 2. In here in column 2 we separate A and B. In the bracket I have put a little plus B here plus C here. What it means is that in the top product you will still have some amount of B. Whatever C that was there in the feed, that would probably come along with B. Okay, so you can see that this is a very simple design where we can achieve reasonable separation of component A, B, C using two distillation columns. And you can see that in terms of the distillation column, they are all very similar. There is a feed for each one of them, there is a condenser for each one of them, and there is also reboiler, there is also reflux. Okay, so you can see there is a reflux for the first column, there is a reflux for the second column. So the actual design of a continuous distillation column is used in both operations. So this is one choice we have, but this is not the only choice. We can have other choices also. Let me take another example of the design. So consider this scheme 2. So here what we are saying is that again the same feed is taken. We design the first column such a way that it only gives product A at the top of the column. Okay, it gives nearly pure A along with some B. Okay, so that is taken out as the product which is rich in A. Whereas again the temperature and pressure of the column can be adjusted such a way that the residue will contain majority of component B and C with a very little amount of A, and this is taken out to another distillation column used as a feed. In the second column we tend to separate component B as the distillate and component C as the residue. Okay, so you can see that same feed, objective is same, we want to separate A, B, C, and you can see the differences between these two designs. Yet again we can have another design. This is a little bit more complicated. So here we have feed A plus B plus C. In the first column we produce a vapor as well as a liquid, which both may have a rich amount of A, B, C in total. Okay, but when this is sent to another column 2, it can be designed such a way that you get 3 fractions, one that is in the top, another one at the middle bottom of the column, and you can also take a cut at the middle of the column somewhere. Okay, so now since we said the relative volatility is A is more than B and B is more than C, and then you can basically fractionate the components at a different locations of the column. Okay, so here you can see that we are also sending a reflex from the second column to the first column, so that this liquid will try to absorb and strip the less volatile component. And similarly here if you see from this column 2, we are also sending partly vapor from second column to the first column. This is because whatever amount of A that is present in this column, when you vaporize, that can come to the first column and use. So you can see that the two column 1 and 2 are very strongly coupled, not only from reflex point of view, but also sending a reflex like thing for a reboiler also. Okay, so you can also think about much more complex design like this, and there are n number of such choices one can make. And like I said before, which one will be successful, which one will be chosen is again determined by the economical considerations and what purity that we want and so on. So in such cases generally we do simulations. Okay, because multi-component distillation is something we cannot do pen and paper or in hand. It has to be done through computer program, because many times these involves a trial and error approach, and you propose a design, you consider the operations, and then you say what is the cost of that, and then you do over many such designs, and then you choose which is more economical. Okay, so that's the design principle generally with regard to multi-component distillation. But one thing you could definitely say is that when we deal with binary distillation, we could separate nearly A and B with single column. When you have n component mixture, here I talked about 3 component mixture, and I have to use at least 2 of them, 2 distillation column here. So you could actually generalize saying that if I have n components and I want to separate these n components in nearly pure forms, you need at least n minus 1 number of distillation columns. So that's the design principle that you will have to follow. You can't do anything less than n minus 1. Okay, n minus 1 is a minimum, and you can see that here in this example. Okay, with the 3 component, in all the designs we had at least 2 distillation column to be used. Okay, so now we will slightly go to another topic, having understood that distillation, multi-component distillation is complex operation. A related concept or distillation is what is called as azeotropic distillation. So azeotropic distillation is actually a special case of multi-component distillation. It's a special case of multi-component distillation. This term azeotrope, it basically means no change on boiling. Okay, it's a Greek word, and it basically means no change on boiling. What it means is that when we boil, the liquid and the vapor will have the same composition. No, there is no change in the composition. Okay, so such mixtures are called azeotrope. Okay, this is a Greek word. We have also seen something like this in the previous lectures, where in some binary mixtures we have what is called this deviation from Raoult's law or non-ideal systems. So what is shown on the top is the TXY diagram, and bottom we see XY diagram of a two component system. So here you can see that this is the boiling point TB, this is boiling point TA. You could have some composition where the vapor and liquid compositions are essentially the same, and it will boils at a temperature less than TA and TB. Okay. So here if you have a binary mixture following Raoult's law, the boiling points will change from TA to TB, that is a range. But when it forms an azeotrope, meaning constant composition in both vapor and liquid, you can have a temperature that is below TA. Okay. So this is what we call as minimum boiling azeotrope. Sometimes we call this as low boiling azeotrope. It also means that you can have other kind of mixtures where this boiling temperature of azeotrope can be higher than TB. Okay, so that we call as maximum boiling or high boiling azeotrope. So this is something we have seen before. I want to just remind about azeotrope means that you will have a composition somewhere here where the equilibrium line cuts the 45-degree line. What it means is at this point the x and y values are the same. Okay, so if you try to distill a system of A plus B following this VLE, you will not have any separation if you do the operation near here. Okay, that is what we mean by no change on boiling kind of a mixture or a constant boiling mixture. So as I said, this azeotropic distillation is a special kind of multi-component distillation, and there are some scenarios where we may want to do azeotropic distillation. Okay, there are two reasons for doing that. One is azeotropic distillation. The reason to do that would be that maybe a binary mixture forms an azeotrope. So why there is an azeotrope, whether azeotrope will always form, these are all determined by thermodynamics, purely thermodynamics, which encodes the mutual interactions and ideality and non-ideality of the constituents. And the azeotrope may be present in certain temperature and pressure, and it may vanish in other pressure. So you have to look at in detail what is the thermodynamics will tell about this binary mixture. Okay. So there are compositions that we know. A very well known example is ethanol water system. It forms an azeotrope at 89.4%. Okay. So beyond that, the purification is very difficult. Okay. So if you don't do anything about it, your distillation will be limited by the azeotropic point. You can't push that purity anything further. But design requirement may say that we want 99% pure or 95% pure. So we need to have some strategy. One of the strategy is this kind of azeotropic distillation, where we want to separate a mixture that inherently forms an azeotrope. There are other scenarios where you may have alpha very low. Okay, the relative volatility between two components can be so small that if you do an ordinary distillation, binary distillation, the number of stages that you need to provide will be very large or very high, and there is a cost associated with that. In such a cases, generally we do what is called this liquid extraction, which will be the topic of the next mass transfer operation. But now let us say you want to fix distillation as the choice of operation. Your alpha is very low. What choices we have? Okay, so in that case we can use azeotropic distillation. So okay, these are the two common scenarios why one would choose azeotropic distillation. One, the mixture inherently forms an azeotrope. Second, alpha is very small even if it is not making azeotrope. Okay, so these are the two scenarios. So the way that we do azeotropic operation is that we generally add a third component. Okay, so you have a binary mixture A plus B. This is what you want to separate. This is our original mixture. This is our original mixture. And then we add a third component. Third component is added, and this third component is called entrainer. So what is the role of this entrainer? What is supposed to do? The requirement is that whatever that we add as a third component or entrainer should make a low boiling azeotrope with one of the constituents of the original solution. Okay, which it means is that if I add entrainer as component C, right, this component C should make a low boiling azeotrope with either A or with B. That's a requirement. So the third component must be chosen such a way that you look at various VLE with A and B and then see which component will form an azeotrope with A or with B. Okay, so the choice of entrainer is limited by the fact that it has to make a low boiling azeotrope. Okay, again recall, low boiling azeotrope basically means that there is an azeotropic composition which boils at a temperature less than the lowest boiling temperature here. So that is one of the requirement. And so let me say, let me also write it here, that the entrainer must produce or form low boiling azeotrope with one of the constituent of the original mixture. Now let us take an example and then illustrate this idea. Let us say I have a mixture of acetic acid plus water, and the boiling point of acetic acid is 118 degrees Celsius and water is 100 degrees Celsius. If you see these two, they do not form azeotrope by themselves. And if you see the temperature difference, the boiling point difference is quite reasonable. One is 100, another is 118. So there is 18 degrees Celsius difference in the boiling point. However, the relative volatility alpha is not very different from 1. It's very close to 1. Okay, so this basically points to the reason that I mentioned here, that there are mixtures which are not azeotropic, but it may have alpha to be very small. So if you try to produce acetic acid water mixture and try to separate, for the purity that you want, the number of stages that you need in an ordinary distillation will be very huge. So generally people don't choose distillation to separate acetic acid from water. There are other methods like extraction and is used. But if you have any limitation about extraction, I will talk about extraction later on, but let us say you want to operate still on distillation. In that case, this is not economical to do by ordinary distillation. So we want to do what is called this azeotropic distillation. For this, we are going to add an entrainer called, in this case, is butyl acetate. So butyl acetate is an ester. Okay, this is an entrainer, and it is such that this butyl acetate is actually very sparingly soluble in water. That means if I have acetic acid in water, it will phase separate. They are not miscible. They have very low solubility. Okay, that's one. The second is butyl acetate and water, they form a low boiling azeotrope. So in short, I will use this as BA, butyl acetate. Butyl acetate plus water forms a low boiling azeotrope. And butyl acetate is very little soluble in water. So, we did not choose randomly the butyl acetate as an entrainer. A lot of discussion goes on to understand the VLE data and so on. So, here for acetic acid water system, people have chosen butyl acetate as a potential entrainer because it serves this purpose of forming low boiling with water, and here water is the high volatile component here, by the way, because alpha is the having the low boiling point here. So, let us discuss this with respect to a diagram. So, this diagram tells discusses shows how we can use acetic acid water azeotropic distillation operation using ethyl acetate. So, you can see that first what we send is a feed containing only acetic acid in water, and the ester is added at the top. Okay, the ester comes here. In this operation, the top product, the vapor that you get, is a butyl acetate water azeotrope. In the bottom, you get acetic acid as a nearly pure product. Okay, the feed contains acetic acid in water. The butyl acetate ester is sent at the top of the column. The operation is such that the top product, the distillate, will be containing ester and water azeotrope, low boiling azeotrope, whereas the bottom one will be the non-volatile or less volatile acetic acid in a nearly pure form. So, this is what you want to actually get as a pure product. It is done. Now, if you look at the top product, what you do is you take this ester water mixture, vapor mixture, and then you send it through a condenser, you liquefy it. When you liquefy, the liquid would actually phase separate into ester rich layer and water rich layer. This is because, as I said before, butyl acetate is very little soluble in water. Okay, when you condense the vapor, in vapor form they are all mixed. Okay, generally in vapor we do not have two phases. Vapor is a single phase mixture, but when you pass it through a condenser and condense the phases, you will see the liquid phase will phase separate into two parts. One part that will be rich in ester with a very little amount of water and very little amount of acetic acid. The bottom layer would be water rich with a very high amount of water, very little amount of ester and acetic acid. In fact, the ester will be saturated here in this. This is ester is saturated in this solution, meaning it will contain as much as it is soluble. Similarly, the ester layer will have amount of water, so that it is based on the solubility of water in ethyl acetate. So, once you have this, you basically send the top layer, ester rich layer, as a reflex to the first column, where it can absorb and stripping, all that operation can happen. Whereas, you have a second column, distillation column, in which the water rich layer is sent such that water is taken as the residue and ester is taken as the top product. And this can be ester water azeotrope on the top can be recirculated back to the condenser, condensate, and then you have a reservoir of the two phases. So, this is an example of how we do azeotropic distillation of acetic acid with water with butyl acetate as a entrainer. Let us talk about another example. Here in this case, I have ethanol plus water. In this case, ethanol water mixture forms an azeotrope at 89.4%. In the previous example, acetic acid water system, there is no azeotrope, but relative volatility alpha is very small. That is why we use azeotropic distillation. In this case too, ethanol water system, there is an inherent azeotrope formation. In this case, we choose a benzene as a entrainer. So, when you have this mixture of ethanol water and then added with the benzene, benzene does not form azeotrope only with water. In fact, it forms an azeotrope where all the three components are present. Okay, this is a little bit more complicated in the previous case. So once you add the benzene, you have a ethanol, I think at about 22.8%, water 23.3%, and benzene 53.9%. So adding benzene to ethanol water mixture forms an azeotrope of this composition, and this azeotrope boils at 64.9 degrees Celsius. Okay. So then what you can do is you can have a distillation column so that the top product comes out as an azeotropic mixture and the bottom product will be ethanol rich residue boiling at 78.4. And then you can take the top product which contains all the three and then send it to a second column, and then you deal with separating ethanol, water and benzene separately. Okay. In fact, if you take the azeotrope, low boiling up azeotrope from the top of the column, when you condense it, you again will have two layers. One will be benzene rich, another one will be water rich. Okay. So you take those two and then separately separate those mixtures. And another related topic is called extractive distillation. Extractive distillation. This is also a special case of multi-component distillation like azeotropic distillation. In this case, what we do is to the binary mixture A plus B having very low alpha, to this we add a solvent. In the case of azeotropic distillation, we add a third component and we call them as an entrainer, so that the entrainer should form an azeotrope with one of the component. In the extractive distillation, on the other hand, we add a third component and we call it as a solvent, and the role of the solvent is to enhance the relative volatility of A to B. Okay. So the solvent is supposed to increase this basically changes alpha to effect better separation, and usually this is very less volatile or non-volatile. Why we say less volatile or non-volatile is because we don't want to vaporize solvent and have extra heat duty. Okay, so you want to have as much less volatile as possible. So in this case, we will take an example of isooctane plus toluene. Okay, this is A plus B binary mixture. This is A, this is B. I think the boiling point is 110.8 degrees Celsius for toluene and 99.3 for isooctane. Here the solvent is phenol. So to see the effect of phenol on the VLE, what you will see is that if I draw XY diagram for isooctane toluene system, Y is the mole fraction of isooctane in the vapor and X is the mole fraction of isooctane in the liquid. This is the 45-degree line. In the absence of the solvent, you will see that this XY data is very close to the 45-degree line. This is what I mean by alpha being very low. Okay. Now, if I add little amount of phenol to the system, this curve becomes little opened up. Okay. So, this is, let us say if I have 55% of phenol added to this. Now, if I increase the amount of phenol to 83, it becomes even better. So, what we are saying is that if I look at the composition of isooctane between the vapor and the liquid in the presence of phenol, the relative volatility of isooctane increases. Okay. So, we know that if alpha is higher, for the same amount of separation, the number of stages required would go down. Okay. So, that is preferred. Okay. So, that is the context. So, in terms of the operation, we have something like this, right. So, in the extractive distillation, we start with a feed containing isooctane, which is A, and toluene B, and then we send isooctane from the top. This is isooctane, and we can, by changing the reflux ratio, we can adjust what percent of acetone is to be refluxed, and there is another stream in which phenol is added too. Okay, you can see at the top there are two streams entering. One is this isooctane as a reflux, but there is also solvent that is added to the top, which is phenol. So, now once you have the mixture of isooctane, toluene and phenol, and the separation is better, and then you will see that at the top nearly pure isooctane comes out, and that can be condensed, taken out as a distillate product, refluxed. And if you look at the bottom product would contain phenol and toluene. Phenol is less volatile because it has a boiling point of 181. Let me go back here, and phenol, the boiling point here is 181.4 degrees Celsius. You can see it is quite high. So, basically it is essentially non-volatile. So, that is why phenol basically comes out at the bottom. We are not vaporizing any phenol here, and isooctane, the less volatile, is taken out at the top, and the phenol and toluene comes out to the bottom, and then it is sent to another tower, second column, where toluene and phenol are separated. Okay. Among phenol and toluene is less volatile, toluene is more volatile and phenol is less volatile. So, toluene is taken out as a distillate product nearly in pure form. It may have little amount of phenol and little amount of isooctane though, whereas at the bottom product here it will be rich in phenol, and this phenol is what recycled to the first column as a solvent. Okay. So, you can see that these two columns are operating in coupled fashion, so that phenol is constantly supplied as a solvent to the top of the column. Okay. And the pure products are taken from the second column, toluene is taken off, from the first column isooctane is taken off, which is what we actually wanted to separate in the first place. So, like I mentioned before, as you can see, dealing with the three component itself gives so much of choices to make, but you may have a large number of components. For example, in petroleum fractionation, you basically have very many fractions that we need to separate. Okay. So, doing a full scale distillation design of an n component system is something you have to do it through computer simulations, Aspen or HYSYS, one of those. For this particular course, we just recognize that multi-component distillations are complex, but we can deal with it by having different combination of binary distillation columns in different topological designs. Okay. So, with that we will stop the discussion on distillation, and after the quiz we will move to another mass transfer operation known as liquid extraction, where in situations where distillation is not permissible or not chosen, liquid extraction is the operation of choice. Okay. So, the design principles will be taught later on. That is all.